Welcome back. So we're going to be looking at past questions for work, energy, and power. Okay, basically we're looking at questions from the WAEC exams and JAMB exams. Alright, so you could, as usual, solve these questions first, test yourself, then come back to follow the video to see what was done and to compare with what you did. Okay, so let's start with question 1. A body of mass 2 kg is released from a point 100 meters above the ground. Calculate its kinetic energy 80 meters from the point of release. Alright, this is from 2019 WAEC. So how do we solve this question? Okay, first of all, let's get out the parameters we have. We have mass to be 2 kg. We have our height to be 100 meters. Okay, and we are asked to find the kinetic energy at the point where it gets to 80 meters away from its release point. Alright, so if we try to imagine this a bit, we have an object here. Let's say it's a box and it's 2 kg. Let's say it's 2 kg and it's dropped from this height to the floor. So let's take this place as the ground. We are made to understand that this distance is 100 meters. Alright, so we are asked to calculate its kinetic energy at, let's take this point to be 80 meters away from So if you have this kind of pictorial representation of this question, okay, you see that the object is 100 meters away from the floor, but they're asking us to find the kinetic energy when it gets to this point here, which is 80 meters away from the point of release. Alright, so to get this, we remember when we talked about conservation of energy, you said energy is not created or destroyed in the universe, but it's converted to other forms. And then we talked about objects undergoing free fall, and we said an object at a certain height, above the ground, has potential energy. If it's not in motion, it has the potential energy at that point is its maximum. Once it is released, that potential energy starts to deplete, it starts dropping, but it doesn't get destroyed, it doesn't get lost. It is just converted to kinetic energy as it's coming down. So since we know that from the class, now if you are to find the kinetic energy at this point 80 meters from the release point, what we need to do is we find the potential energy at this release point, alright, and find the potential energy here. The difference in that potential energy is the kinetic energy at this point, because of course the potential energy decreases as it gets to this point, but that potential energy is not lost, it is converted to kinetic. So whatever the difference in potential energy is between these 2 points will be the kinetic energy at this point. So that's basically what we did to solve the problem. So we have potential energy at 100 meters, that's at this point, is mass times gravity times height, which is 2 kg times 10 meters per second squared for gravity and 100 meters for height, that we know. If we simplify that, we're going to get 2000 joules. Now let's find potential energy at 80 meters from release point. If we'll find the potential energy here, it means we have to find the height of this place from the ground, which is 100 minus 80, which is 20 meters. So we're going to use 20 meters as our height. We use same formula mgh, which gives us 2 kg times 10 meters per second squared times 20 meters, which is 400 joules. So now what do? We find the difference between both of them, and that will give us the kinetic energy at 20 meters. Alright, so PE lost is 2000 minus 400, which is equal to 1600 joules. So that gives us the kinetic energy at this point. Second question. A car traveling at 30 meters per second overcomes a frictional resistance of 100 newtons while moving. Calculate the power developed by the engine if 1 horsepower is equal to 0.75 kilowatts. This is kind of a refresher of what we did in the fourth lecture, where we talked about friction. So remember we said that when an object is static and a force is applied on it to make it to begin to move, the force has to first overcome the frictional force, but in that case, the static frictional force. When an object is already in motion, all right, and we want it to continue in that motion, we have to continually overcome the dynamic friction. Otherwise, that object will be brought back to static position. In this case, the car is moving, all right, at a particular speed, and we are asked to find the power developed by the engine. Of course, this power developed is going to be the power from the force the engine is applying to overcome the frictional resistance. Okay, so if that is the case, all right, we will take the frictional resistance of 100 newtons as the force applied. Okay, because that's the force that, of course, we are expected to, the car engine is expected to overcome to keep this car moving at 30 meters per second. So we have our parameters. We have V, which is the velocity at 30 meters per second. We have our frictional force to be 100 newtons, and we're asked to find the power the engine, okay, exerts. Okay, we know that power is work done over time, and work done is force times distance over time. So if we look at this carefully, we'll see that distance over time is actually velocity. So our velocity here can replace distance over time. So if we do that, we'll have our power to be force times velocity. Now the force in question here is the frictional resistance. Okay, the force of the frictional resistance, because that is the force that we need to apply on the car to overcome the frictional resistance for it to move at this speed. So we are taking that force as a force the car is applying. Okay, so we can use that force to find the power the car exerts. So we have 100 newtons times 30 meters per second, and that gives us 3000 watts. All right, if you look at our units here, the unit here is Newton meter per second. Okay, and if you check the formula to confirm, you will find out that yes, Newton meter per second will give us watt. So we are actually very correct. So that's the way you can also check to be sure your calculation is right. So since our answer is supposed to be in horsepower, we have 1 horsepower to be 0.75 kilowatts. All right, so we convert it to horsepower from the kilowatt or the watts. So what we do here is simple. Since 0.75 kilowatts is 1 horsepower, 3000 watts will be 3000 times 1 horsepower divided by 0.75 kilowatts. Okay, if we do that, if we simplify that, of course we're going to have 4 horsepower. Okay, so that's it for question number 2. Let's move on to number 3. A carpenter on top of a roof 20 meters high dropped a hammer of mass 1.5 kg and it fell freely to the ground. The kinetic energy of the hammer just before hitting the ground is from JAM 2011. Okay, so of course we have parameters to be height, which is 20 meters. Okay, we have mass to be 1.5 kg. We have to find the kinetic energy. All right, so I think this is a very simple one. All we need to do is to remember same analogy we used for question 1. You know, when an object is a certain height above the ground, it's still, it's not moving. It has its maximum potential energy at that height. Once it starts coming down, the energy gets converted from potential to kinetic. Once it's about to hit the ground, you have the maximum kinetic energy at that point. So if you're asked to find the kinetic energy of the hammer just before hitting the ground, it's the same thing as asking us to find the potential energy of the hammer at the height, okay, where it was, because it's that potential energy that would get converted to kinetic energy at the ground level just before it hits. Okay, so knowing that kinetic energy just before hitting the ground is potential energy at 20 meters above ground. All right, so we bring in our values. Okay, knowing that kinetic potential energy at 20 meters above ground can be found with mass times gravity times height. So putting in the parameters into the equation, we have 1.5 kilograms times 10 meters per second squared times 20 meters, and that will give us 300 joules. All right. Okay, so we move on to number 4. From the diagram above, calculate the work done when the particle moves from x equal to 0 meters to x equal to 80 meters. All right, so we have this particle moving from this point to this point, but this is a force distance graph, and we're asked to calculate the work done. Okay, so we know that first of all, work is force times distance, and we have a force distance graph. Let me just give us an easy way to think about quantities and the graph. In fact, once you have a graph like this, you have a quantity on your y-axis, you have another one on your x-axis. Okay, now if you want to find out a quantity from this graph and it involves the multiplication of the y-axis and the x-axis, what you need to do is simply find the area under the curve. If it has to do with division, all you need to do is find the gradient of the curve. Okay, so that's an easy way to deal with graphs and getting information from graphs for your quantities. Okay, but then here we're asked to find we're asked to find the work of this body from the graph, and we have force times distance. So automatically you just know you're finding the area under the graph. And we know that we're not asked to find the work he did going through this journey. We're asked only for the work he did from the point 0 to point 80, all right, 80 meters. And then we know we have this triangle here. Okay, we have a triangle here for that distance. So what do? We find the area under the curve, which means we're finding the area of the triangle, and the area of a triangle is half base times height. So if we bring out the formula and put in our parameters, we're going to have half times 80 meters times 60 newtons. Okay, so that would give us 2,400 joules. All right, so that's how easy it is to solve this question. So we move on to number 5. Our question is, if a pump is capable of lifting 5,000 kg of water through a vertical height of 60 meters in 15 minutes, the power of the pump is... Okay, so we have our parameters as mass equal to 5,000 kg, we have h equal to 60 meters, and we're asked to find power. Okay, so we know our force is normally mass times acceleration, and the acceleration in this case is the acceleration due to gravity, because of course this is talking about lifting. Okay, so we have 5,000 kg times our acceleration due to gravity, which is 10 meters per second squared, times 60 meters, okay, divided by our time. Okay, 60 meters here is our distance. All right, then we divide everything by our time, which is 15 minutes. Okay, but then we have to change that to seconds, so we multiply it by 60 to get our answer in seconds. So if we simplify this, we have 3.33 times 10 raised to power 3 joules per second. Look at number 6. Find the potential energy of an object of mass 10 kg placed on the building floor 10 meters above the ground level, and we have g as 10 meters per second squared. Okay, so we bring out our parameters from the question. We have mass to be 10 kg, we have height to be 10 meters, we have potential energy to find. Okay, so what do? Potential energy is simply mass times gravity times height. So we take our mass, multiply it by gravity, and then multiply it by the height of 10 meters, and we simply find the potential energy of the object on a building floor. Okay, so that's 1,000 joules. So we'll go to question number 7. What is the cost of running 7 40 watts lamps and 5 80 watts lamps for 12 hours if the electrical energy cost is 7 kilowatt hour naira? Okay, so basically what we need to do here first of all is, of course, we're trying to find how much this house would spend running 7 40 watts lamp and 5 80 watts lamps. Okay, so we have to first of all find the power consumed here. Okay, so to find the power consumed, we have to get multiply 7 by 40 to know how much power was consumed here, and 5 by 80 to know how much power was consumed. So if we do that, we would have total power consumed to be 680 watts. Okay, so 40 watts times 7 pieces of bulbs, 80 watts times 5 pieces of lamps. Okay, we have that to be 680 watts. All right, so now we need to know how much kilowatt hour was consumed. From the class, we remember that 1 kilowatt hour is the amount of kilowatts consumed in 1 hour. So we're about to find how much kilowatt was consumed in 1 hour by this building with this equipment. So we have total kilowatt hour consumed is 680 watts times 12 hours. Now if we do this, we find our answer to be 8.16 kilowatt hour, which means this building consumed 8.16 kilowatts every hour, every single hour. Okay, so if we now get to find the total energy consumed, since we have 1 kilowatt hour to be 7 naira from the question. If we multiply 8.16 kilowatt hour, all right, by 7, we're going to have the total amount this building would spend running these lamps. So if we do that, we're going to get 57.12 naira. Okay, so that gives us the total amount spent by the owner of the house. Okay, so question number 8. A man weighing 200 newtons runs up a staircase in 5 seconds. If the height of the staircase is 9 meters, calculate the power of the man. All right, so this is another easy case. We have our parameters to be 200 newtons for weight, 5 seconds for time, 9 meters for height, and we're asked to find power. We know power is work done over time, which is same as force times distance over time. Okay, so this man weighs 200 newtons. That 200 newtons weight is the force, okay, that we need to calculate the power he spends, okay, because this weight here comprises of his mass and gravity. Okay, remember, weight is found from mass times gravity, okay, and that is mass times acceleration due to gravity, which is force. So this weight is our force. Then distance is the height, which is 9 meters, and our time is 5 seconds. So if we do that, bringing the parameters into the equation, we have 200 newtons times 9 meters divided by 5 seconds. And if we simplify that, we have that the man exerts power worth 360 watts. Okay, so that's it for today. Thank you for joining.